repeat myself since the camera wasn't on the first time. Blue line, if you took that path from A to B, the blue line is your distance traveled, the red line is your displacement. And the units for both of those are meters. Right. Speed versus velocity. Speed is distance per unit of time. Velocity is speed plus a direction or displacement per unit of time. So usually velocity and displacement have a direction associated with them. Speed and distance do not. A lot of times these will be used interchangeably for this part because everything's in a straight line. So if everything's in the same direction, speed and velocity are the same thing. Alright, units for both are meters per second, and velocity is abbreviated with lowercase v. Instantaneous speed versus average speed. Instant speed is how fast you're going at a given instant. Average speed is how fast you travel over a whole trip. So average speed is distance over time. Do you guys want a hole punch? Anybody? You can pass it around. Alright, just some questions here. This is a tough one. What is the average speed of a cheetah if it sprints 100 meters in 4 seconds? So you guys can just shout it out. 25 meters per second. How about if it sprints 50 meters in 2 seconds? 25 meters per second. You start from rest and accelerate to 80 kilometers per hour. Would it be possible to have an average speed of 80 kilometers per hour if you never travel faster than 80 kilometers per hour? No. Why not? Because you started at 0. So you're going less than 80 for some amount of time. So in order to get your average speed to above 80, you'd have to go, or to 80, you'd have to go above 80 at some time to cancel that slower part out. Does that kind of make sense, everyone? Right. The speedometer of a car moving to the east reads 100 kilometers per hour. It passes another car that moves to the west at 100 kilometers per hour. Do both cars have the same speed? Yes. Do both cars have the same velocity? No. Everybody understand that one? During a certain period of time, the speedometer of a car reads a constant 60 kilometers per hour. Is a car moving at a constant speed? Constant speed. Is it moving at a constant velocity? Possibly. We don't know. We don't know if it's turning or changing directions at all. If it changes directions, the velocity changes. So it is moving at a constant speed. We don't know if it's moving at a constant velocity. In a drag race, is it possible for the car with the greatest speed at the end of the race to lose?
Yes.
Yes. If it accelerates more slowly, like if one car accelerates quickly to its top speed, and the other car accelerates more slowly to its top speed, the one that accelerates very quickly to its top speed will win. Does that make sense? Even if that top speed is lower. Does the speedometer of a car measure the instantaneous speed or the average speed? Instantaneous. The duck had an average velocity of 0 meters per second over a time of 3 minutes. What can you say about its displacement?
There was no displacement.
There wasn't displacement. Displacement was 0. What can you say about its average speed? Not necessarily. We don't know what its average speed was. So there's two options for the duck to have a velocity of 0 meters per second and displacement of 0. It could have stood still for 3 minutes, or it could have walked in a circle for 3 minutes. So if it walked in a circle for 3 minutes, its displacement would be 0. But would its speed be 0 for that time? No. So we don't know about the average speed in this case. Everybody understand that? You're riding your bike. This is my favorite one. You're riding a bike on a 10-mile long path. You travel the first 5 miles at a speed of 5 miles per hour. How fast do you have to travel over the next 5 miles for your average velocity to be 10 miles per hour? Nope. Alright, this one needs an explanation here. Okay. If you want to, on a 10-mile trip, if you want to average 10, or how far do you go in the whole trip in this case? 10 miles, or distance 10 miles. If you want to complete that with an average speed of 10 miles per hour, how long do you have? 1 hour. So your time is going to have to be, you have to do those 10 miles in 1 hour. How long did it take you to do the first 5 miles at 5 miles per hour? 1 hour. So how much time do you have left to finish the last 5 miles? None. So it's impossible for your average speed to be 10 miles per hour in this situation. So you'd have to go infinitely fast. Does everybody understand why? And the one thing that this kind of illustrates is if you traveled at 5 miles per hour for 1 hour and 15 miles per hour for 1 hour, then your average speed would be 10 miles per hour. But if we traveled at 5 miles per hour for 5 miles and 10 miles per hour, or at 15 miles per hour for 5 miles, that's not the same. Because which would you spend more time doing? And if you, let's say for the second 5 miles you traveled at 15 miles per hour, which would you spend more time doing, going 5 or 15? 5. So your average speed would be closer to 5 than it would be to 15 because you spent more time doing 15. Does that make sense to everybody? Alright. Since velocity is the change in position per unit of time, what do you think is the equation for velocity? What over what?
Speed over time.
That's speed over time. Change in position is what? Is that distance or displacement? Displacement. So what's the equation for velocity? Displacement over time. And it's usually going to write displacement as delta x. Alright, acceleration. Acceleration is measuring the rate the velocity changes. So acceleration is equal to the change in velocity or the change in time. So it's going to be final velocity minus initial velocity over the time it took for that change. Because acceleration involves a change in velocity, a change in direction will also cause there to be an acceleration. We're not going to deal with change in direction causing acceleration quite yet. That's going to be later on this year. The units for acceleration are meters per second, but they're usually written as meters per second squared. And so what a meter per second means is that every second you're going 1 meter per second faster. Does that make sense? So if your acceleration is 1 meter per second squared, that means every second you're going 1 meter per second faster. If it's 2 meters per second squared, every second you're going 2 meters per second faster. You guys understand that? And acceleration is going to be abbreviated with the lowercase a. Alright. A particular car can go from rest to 90 meters per second in 10 seconds. What is its acceleration? What's the change in velocity? Went from 0 to 90, so what's the change in velocity? 90. So what's the acceleration? 9. So it's just the change in velocity over the time, so it's 90 over 10. Does that make sense, everybody? Alright, in 2.5 seconds, a car increases its speed from 60 kilometers per hour to 65 kilometers per hour. while a bicycle goes from rest to 5 kilometers per hour. Which undergoes the greater acceleration? They're the same. Does that make sense, everybody? The change is the only thing that matters, not the speed. Right, what is the acceleration of a car that drives past you at a constant velocity of 400 kilometers per hour?
There's no change.
There's no change, so 0 meters per second squared would be the acceleration. Okay. Which has the greater acceleration, an airplane that goes from 1,000 kilometers per hour to 1,005 kilometers per hour in 10 seconds, or a skateboard that goes from rest to 5 kilometers per hour in 1 second? Skateboard. Everybody understand why it's the skateboard? It's the same change in velocity, but over a shorter amount of time. So the acceleration of the plane would be 0.5. The acceleration of the skateboard would be 5. Right. Can an object have a westward acceleration while traveling east? Yes. What's happening if that's going on? Deceleration, so it's slowing down. So if you're traveling east and your acceleration is west, you're slowing down. So if the acceleration was 1 meter per second squared again, you'd be slowing down by 1 meter per second every second. Does that make sense to everybody? Alright, can an object be increasing its speed as its acceleration decreases? Yes. So the acceleration can be going down but still positive, and it will still be speeding up. It'll just be speeding up at a slower rate. So like if you're going 10 meters per second and you're accelerating at 5 meters per second squared, after that second you'll be going 15 meters per second. Your acceleration goes down to 4 for the next second. After that second has passed, now you're going 19. So even though your acceleration went down, your velocity will still be going up as long as it's above 0. Does that make sense to everybody? Right. Since acceleration is change in velocity per unit of time, what would the equation for acceleration be? Change in what over time, John?
Delta V over T.
Delta V over T. So it's change in velocity over time, and delta V is usually going to be final velocity minus initial velocity. Alright, our equations for this stuff. When you're moving at constant velocity, your velocity is just displacement. It's usually, in this case, you can always interchange distance for that as well. Displacement over time. Does that make sense? You can only use that if there's no acceleration or constant velocity, which means the same thing. So if you're doing a problem and it says constant velocity or there's no acceleration, use this equation. If there's a part of a problem that there's no acceleration for. For constant acceleration, there's these 4 equations. And these should be like, they're not negative signs. Every year I think I should change those, I never do. So those are like dots, not negative signs. So in this case we have distance or displacement equals 1/2 times the quantity final velocity plus initial velocity times time. Delta x equals initial velocity times time plus 1/2 times acceleration times time squared. Final velocity equals initial velocity plus acceleration times time. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Do these look bad right now? It's really, when you first start this stuff with the math part, and probably on Monday next week, this stuff will seem awful. Not for everybody, but for some of you it'll seem awful. When we come back to it and review for the exam in December, you'll be like, why was this hard? don't know if that's good or bad because it means the class gets harder, but more than anything, you guys get used to doing stuff like this. It looks bad now, like as you look at these equations, but it won't be in 2 weeks. You might have some frustration and want to like stab your paper in the next 2 weeks, but it'll get better, I promise. Does anybody have any questions on what any of these things mean? And most of these equations are derived from calculus. How many of you guys are in calculus in here? Almost everybody. Most people. You don't need to be in calculus to be in here, but periodically, once you guys get to derivative and stuff like that, I'll go through some of the physics concepts with the calculus base, and those of you who aren't in calculus can just ignore me for like 10 minutes. But it'll help you understand calculus a little better. And you can also sometimes trick me into helping you with your calculus homework. Alright, so like I said, I promise these equations look like gibberish right now. They'll make sense once we start doing problems. They may look like gibberish for a couple days still after that, but it'll get better. Alright. Alright, free fall is a specific kind of acceleration where things are moving vertically. So like if I drop this marker, it's in free fall. That makes sense? So it's when there's only gravity acting on it. Even if I throw it up and it comes back down, that whole time after it left my hand it was in free fall. Alright, so some important things about free fall. The acceleration is always negative 9.8 meters per second squared, and that's going to be represented by a lowercase g. So whenever you see a lowercase g in here, it means 9.8 or negative 9.8 meters per second squared. We're going to use down as the negative direction, up as the positive direction, and we ignore any air resistance for right now. We won't always be doing that, but for right now we will. Right, so in free fall, drop it from rest, it goes faster every second. And it goes faster every second by 9.8 meters per second squared. So every second it gains 9.8 meters per second. And what happens to the distance it falls each second because it's accelerating?
Each time it keeps falling farther.
Yep, so the distance increases as it falls as well. Does that make sense to everybody? Alright, some important notes. This is probably the most important thing. Now, these are the two most important things that you guys will mess up on and ask me about, and you'll get stuck in a problem because of. The velocity at the highest point when something's going up is 0. So as something goes up, it stops, it goes to 0 meters per second for a brief amount of time, then comes back down. It's very useful, like if I want to figure out if I throw something up, how long does it take to get to the top of its flight? I can say my final velocity is 0 at the highest point. Does that make sense to everybody? What's the acceleration going to be at the highest point, though? In free fall, the acceleration is always negative 9.8 meters per second squared. So at the highest point, the velocity is 0, but the acceleration is still negative 9.8 meters per second squared. What would happen if the velocity was 0 and the acceleration was 0? It would stay there. That's obviously not what happens. So you still must have to have acceleration. Makes sense. So the velocity goes to 0, but the acceleration stays negative 9.8. And this is more of kind of a practical one. If I drop this, we talk about the final velocity of it. We're talking about the velocity the instant before it hits the ground. Once it hits the ground, it's 0, obviously. But we want to use the speed it hits the ground with as our final velocity when something's hitting the ground. Does that make sense to everybody? So your final velocity when it's hitting the ground is never going to be 0. Alright, so the equations for free fall, very similar to the equations for, and these again shouldn't have negative signs in front of them. There should be dots. The equations for free fall are the exact same as the equations for acceleration. Only difference is delta x has been replaced with delta y since we're moving in the vertical direction now. And A has been replaced with G. So in some ways these are easier, but we end up with sign issues and stuff like that, which we'll see when we get to these problems. But these are what the equations are. Like I said, they look ugly now, but they'll be better later, I promise. Alright. First free fall question. What is the gain in speed per second of a freely falling object? Mm-hmm. 9.8. So it gains 9.8 meters per second every second. It's just kind of weirdly worded question. Right. With what velocity does a dropped object hit the ground with if it falls for 1 second? 9.8 meters per second. So if it's falling for 1 second, it's gained 9.8 meters per second of velocity. An object is thrown upward with a velocity of 19.6 meters per second. How fast is it moving after 2 seconds? So if I start throwing it upward at 19.6, is it gaining velocity or losing velocity as it goes up? Losing. How much does it lose every second? 9.8. So if it loses 9.8 every second and it's 2 seconds, how fast is it moving? Start 0. 9.8 times 2 is 19.6. Alright. Graphing motion, we're actually going pretty fast here. Alright. Graphing motion, position versus time graphs. If we have constant velocity, this is what the graph looks like. So this is a car moving at constant velocity. What's its velocity in this case? 10 meters per second. Every second it moves 10 meters. So if we have a position versus time graph of this, it's a straight line. And that means it's moving at a constant velocity. If we position versus time graph is a straight line, it's constant velocity. Does that make sense? Right, accelerated motion. This time we have every second we're going faster. How much faster are we going every second? What's the velocity at 1 second? For that first part. 2. What's the velocity of the second second?
8.
Velocity here is going 8 meters in 2 seconds, so it's 4. So every second it's going 2 meters per second faster, so the acceleration is 2. When you have accelerated motion, the position versus time graph is a curved line. So what do you think the slope of this line represents in both cases? Let's go back here. What does the slope of this line represent? Velocity. So the slope of this, what's the slope of this line? It goes up 10, 10. So the slope of this line is 10. So that means the slope of the line and the velocity are the same thing. If we look at this one, what's happening to the slope of a curve? Is the slope staying the same or changing? Changing. Since our object is accelerating, is our velocity staying the same or changing? Changing. So if we have something accelerating, the slope of the graph changes and the velocity of the car changes. Does that make sense? Alright, constant velocity on a velocity versus time graph is just a straight line. So if we're moving at 10 meters per second on a velocity versus time graph, our line is just a flat line. What's the slope of this line? 0. So, what do you think the slope of that line represents? Do you have any guesses? What's the acceleration of the car? 0. What do you think? The slope of the line is 0. What do you think the slope of the line represents? Acceleration. So the slope of the line of a velocity versus time graph represents acceleration. So now we have accelerated motion. What's the slope of this line? 4. So the acceleration of the car is 4. Does that make sense to everybody? Alright. We're going to stop there for today. You guys done? And we'll just do that. We have a couple of graphing motion questions. And we'll probably start the math a little bit on Friday and finish it on Monday. How do you guys feel right now?
Alright.
How many people feel okay, at least? Anybody feel awful? Bad?